Okay, so what I want to cover now is analog to digital converters. And the reason I do that now is it's going to kind of set a practical example that we're going to fit some future circuits to. We're going to create some future circuits for the sake of interfacing with this very popular peripheral. Now, an analog to digital converter is a peripheral, and you find them built into microcontrollers, as well as you find them as standalone devices. So we're going to cover kind of the externals, how you sort of interface and work with an ADC, what it does, and we'll look at one of the most popular ones, one of the most popular types, and how that operates. So let's go ahead and set it up. I've created just a block here that is our ADC, analog to digital converter. And when you go ahead and talk about an analog digital converter, you need to specify what we call the resolution. And I'll get into, setting up those numbers a little later. For right now, we're going to work with an 8-bit ADC. Okay, you can have an 8-bit ADC, you can have a 10-bit ADC, 12 bits, 4 bits. I mean, you name it, there's an ADC that's out there. Now, the whole goal of an analog to digital converter is to take an analog voltage. So it's taking a voltage that could be 0 volts, 0.1 volts, 0.2 volts, 3 volts, 5 volts, 4.566, 7 volts, any voltages on this continuous range. Now remember, an analog voltage really is continuous. And it's going to convert that continuous voltage, whatever value it's at, into a digital or discrete value, a number that's represented by a sequence of zeros and ones, right? So that's why over here we have one wire that's going to take a voltage on the range of 0 volts to 5 volts, and it's going to, through some process, convert that into a number, a numerical value that's represented in digital or in binary. And for our purposes, since this is an 8-bit analog to digital converter, it's going to convert whatever voltage is here into this range of discrete values going from hex 00 all the way up to hex 0xFF. So you can think of 00, you can think of this range. 00 refers to 0 volts, and FF refers to 5 volts. And we'll see how that conversion is done, both from just a math point of view, numerically, and also how the ADC works on the inside to achieve this. Now, I do want to compare and contrast this just for a brief second, that when you think of your microcontroller or your FPGA or any digital device, typically these wires, or I should say, if you don't have an ADC, these wires can only represent, each one of them can only represent either a 0 or a 1, either 0 volts low or 5 volts high. This is for a microcontroller that's being powered from 5 volts, typically. Okay, I just gave 5 volts in ground in order to say that this microcontroller is indeed working with 5-volt logic, and so a high refers to 5 volts and a low works with 0 volts. So one wire can only take on 2 states. But up here with our analog digital converter, one wire can represent a range of values going from 8 bits, 00 hex, all the way up to an 8-bit all ones FF. Okay, so that's kind of the goal here of what this analog digital converter is attempting to do. Now, let me give a little prelude on analog digital converters. Analog digital converters, I'm going to say, is one of my favorite topics, one of my favorite devices. You'll see why in a second. It really gets to the heart of embedded systems and embedded systems design. Now, I don't know how many different embedded systems I've created over the years, but it's what I've been doing for the past, I'm getting old, 15 years now. A little less than that. 13 years, let's say. Okay, now not one embedded system I've ever worked on hasn't used an analog digital converter. And there's a good reason for this. Now, embedded systems, as opposed to like your standard computer or any general purpose computing device, almost always interacts with the real world. Embedded systems are small devices that interface directly with the real world. And the real world is not digital. The real world always comes into our system as an analog value, as this continuous range of values. And we're attempting to do some type of numerical computation on those real world processes. And to do that, we need to convert the analog domain into the digital domain so that we can do numerical computations on that. Now, the physical world that we deal with, that we can touch and feel and sense and perceive, is truly analog. And I'm going to go over some examples here. I'm going to list out a bunch of physical quantities, and then I'm going to list how we take those physical quantities and turn them into something that we can perform useful and meaningful calculations on. Now, the easiest to visualize is probably that of sound. Sound that we hear is just a pressure wave traveling through some medium, air or a table, or some sort of matter. And it's always some combination of frequencies that's represented with sine waves, but it's a continuously changing or continuous varying signal, meaning it's not discrete, it's not digital, it's not a 0 or a 1, it's everything in between 0 to 1 and 0 to -1, or however you represent it. But it is every single, an infinite series of points going from our smallest value to our largest value. So a sound wave is some sinusoidal signal. So our sound waves are analog in nature. Now, other physical quantities of interest that embedded systems generally would like to work with, another one is going to be that of light or electromagnetic radiation. So again, light can be represented with sine waves, with continuously changing and varying analog values. Other ones also in the electromagnetic spectrum would be that of radio waves. Temperature is another one. If you think about temperature, you don't just have 100 degrees and 101 degrees, you have 100.1 degrees and 100.12 degrees and 100.2 degrees and 100.3, so forth. It's again a continuously time varying signal that is analog. Pressure is also another one. Think about all the data acquisition that occurs when you're creating a crash test dummy. I use this as an example because I actually have a friend who owns a company that makes crash test dummies for NASA, and they have these pressure sensors that detect how much force is exerted on different body parts under varying conditions. So again, that would be a type of embedded system. And it would be working with taking measurements from pressure sensors. Wind speed, earthquakes, etc., all of these physical quantities come to us in an analog form, and if we're going to fulfill our goal of being a computer engineer, especially if you're working with embedded systems, FPGAs or any other type of system, you're going to be interfacing with this real world. Now, associated with each one of these physical quantities is going to be a corresponding sensor. Now, we generally say the word sensor. If you want to sound smart, you're going to say the word transducer. Transducer is going to be the more proper technical jargon when you're in the workplace. So please, when you're going to an interview and you talk about some device you made that has some sort of sensor, and say transducer instead. It's just, you're going to come off a little more professional. So in the case of your physical quantity of sound waves, you're going to be using a microphone as your transducer. If you're working with light, electromagnetic radiation, then how do you get that into a computing system? You're going to be using some sort of phototransistor or a photodiode or a cadmium sulfate cell. And I'll go ahead and list those. A cadmium sulfate, cadmium is a type of resistor that changes its resistance. So the resistance changes based off of how much light actually hits the transducer, or how much light hits the cadmium sulfate cell. You also have photodiodes. Notice my light ray is now entering the photodiode, and the photodiode changes the amount of conductivity between the anode and the cathode based off of how much light actually hits the diode. So this would be a photodiode. And another type of light sensor is a phototransistor, who changes the amount of, again, the amount of conductivity between the collector and the emitter based off of how much light actually hits the surface of the sensor or the surface of the transducer. So 3 different ways of turning light into an analog value. Okay, in the case of radio waves, your antennas. Another type of antenna is a satellite dish. Satellite dishes are just antennas. They output, an antenna outputs a very small analog value based off of how much electromagnetic radiation hits that. And antennas are tuned for specific frequencies. So when you're talking about like your FM and AM radio waves, you have a certain length antenna that actually resonates at those frequencies of interest. So an antenna and satellite dish, those are your transducers for radio waves. For temperature, we have thermistors. Thermistors are resistors that change the amount of resistance in response to the amount of temperature. So if it gets hotter, typically many thermistors actually increase in resistance when their temperature goes up. There's also another device called a thermocouple that actually generates a small voltage that's proportional to the amount of temperature it's at. For pressure, we have pressure transducers. These are they're called strain gauges, and these are little resistive elements that again change the amount of resistance based off of how much pressure is being exerted on the physical device. Wind speed, earthquakes, etc. Every physical quantity has some group of transducers capable of turning them into analog quantities. So I list this just to increase the scope of what we have as potential in order to get signals into our systems. Now, getting back to our analog digital converter, we can take a signal from any one of those transducers and turn it into a binary value. That's the whole goal of this analog digital converter. Now, one of the first things that we're going to need to specify is the resolution. So when you're talking about resolution, you're going to be saying whether it's an 8-bit ADC or 10-bit or 12-bit, 16-bit, etc. The resolution tells us what the output from the analog digital converter is. Now, the more bits that we have, the more precise of a measurement we can take, the more accurate the analog digital converter is. Now, for the sake of keeping this easy at first, we're going to stick with 8 bits. Now, given each one of these each one of these resolutions, we can specify the number of steps. So for an 8-bit analog digital converter, how many different steps do we have? Well, if we go ahead and take 2 to the 8, 2 to the 8 is equal to 256 steps. Ten bits gives us more steps. 2 to the 10 gives us 1024. And so forth. 12-bit gives us 4096. And 16-bit 65536. Now, That gives us our resolution, which tells us what our possible outputs could be. However, we need to also refer to this input. So our input is a range. So we need to map our input range to our output range. For that, we're going to specify the step size. Step size is the smallest change that an ADC can measure. So if we're sticking with our example of an 8-bit analog digital converter that takes an input of 0 volts to 5 volts, we can calculate what the step size is going to be. The resolution is 8 bits. The number of steps is 256. And our step size is going to be 5 volts divided by how many steps we have to represent that 5 volts. So the smallest change that can be measured with this analog digital converter of 8 bits is going to be 19.53 millivolts. So let's go ahead and show what the value would be converted into. So let's go ahead and take our ADC. We have one wire coming in that can take on a value of 0 volts to 5 volts, and it spits out a discrete number that can take on a value range of 0x00 all the way to 0xFF. Now, I'm going to start with the min and max of this, and I'll list them out below. Zero volts. What should this analog digital converter convert 0 volts into? 0x00. And similarly, the largest value of 5 volts, what should that get converted into? Well, it should be 0xFF. Let me split it down the middle. What should 2.5 volts get turned into? Well, it should be half of 256. This is actually 255. 0 to FF. So halfway should be 0x80, or 128. What about 1 volt? Well, now we're going to have to start looking at that step size. Now we calculated the step size by taking this range, so the difference here being 5 volts of range, and dividing how many numbers we can cram 5 volts into, and dividing it by 5 volts. So our step size equaled 5 volts divided by 0 to FF is 256 different values. Which we got 19.53 millivolts. So if we want to know what the analog digital converter is going to convert 1 volts into, all we have to do is take 1 volt and divide it by our step size. So 1 volt divided by 0.01953, or 19.53 millivolts, gives us 51.2. However, 51.2 isn't a digital value. This 0.2 is kind of messing with that. So we lose that 0.2. Just go ahead and round it. Now, there's a good question here, which is 51.2. Is that 51 or is it 52? Because this 0.2 obviously can't be represented with 8 wires in an 8-bit digital value. So what happens to our fractions? Well, to answer that question, kind of depends on the type of ADC you have. Different ADCs manipulate this fraction a little differently. And so I can't give you an answer as to what this ADC is going to do. Is it going to always go to the ceiling? Is it always going to go to the floor? Or is it going to round it? I don't know. It depends on the topology. It depends on the internal workings of this ADC. Now, we'll see what happens to a fractional value a little later in the specific topology that I'm going to cover for the most popular, I would say, type of analog digital converter. But for right now, just round it. I'm fine if you just lose the decimal as well. I mean, both would be correct because I haven't specified what type of ADC this is. But I don't want it to get in the way. So just round it or just take the floor of it. It doesn't matter to me. Okay, what about if we gave our analog digital converter a value of 2.1 volts? What does that get converted into? Well, that's going to get converted into 2.1 volts divided by 19.53 millivolts, which is going to equal 107.5. Again, I don't care about this fraction. So it turns into 107. By the way, if you put 108, I would consider that to be correct as well, because again, I haven't specified the type of analog digital converter. So that's how you go ahead and calculate what your value, what your output is going to be for a given input. You just take your input, divide it by the step size, the smallest value, the smallest change that an analog digital converter can measure, and you get out your digital value from there. What about if we were going to go in the other direction? What if I had a conversion that gave me a value of, let's see, pick one. Let's say I got the number 123 base 10. So from 0 to 255, I got the number 123 on the output from this digital converter. What was the voltage? Well, to do that's pretty straightforward as well. You just multiply by your step size. So 123 times 19.53 millivolts equals what? 0.01953 times 123. Okay, apparently we got a voltage on the input that was equal to 2.4. What about if we ended up with a converted value of 240? Now 240's getting up there. It's not that far off from 255. I expect that our value is going to be in the neighborhood very close to 255. Well, just take the number 240, multiply it by our step size, .68 volts. Okay, sorry, I had said close to 255, the opposite. Close to our upper end of 5 volts, which it came out to be 4.68 volts. Okay, so if you want to know the digital output for a given input, you just divide by your step size. And if you want to know analog input, for a given result or a given output, you just multiply by your step size. Okay, so pretty straightforward. And that kind of defines what our input gets mapped to as far as our output. Now, next that we're going to look at is how an analog digital converter achieves this. Now, I'm going to say that there are actually two common types of analog digital converters. One of them is called successive approximation, and the other one is called flash. We're going to not cover flash. We're going to only look at successive approximation, or SAR, a SAR converter. Now, I'm going to actually cover this in the next video. All right, take care. All right, so now we're going to go ahead and go over how the successive approximation works for an analog digital converter. Okay, so the SAR type analog digital converter is the most common, and it's got a good trade-off to speed and accuracy, and also it's fairly straightforward to construct one. So we're going to go over that one since it is the most popular. Okay, now here's kind of the topology or internal workings of an analog digital converter, specifically the successive approximation type. Now, we need to go ahead and kind of point out what these blocks are. Now, these blocks in and of themselves are not components per se, though they could be. Mainly, when you create an analog digital converter, when the manufacturer creates one, they put it into one single chip. We usually call that like a monolithic chip, or monolithic integrated circuit, IC. And so all of this would be constructed inside, and the finished product would be what we kind of showed earlier with just the block. Having an analog input, your digital output, and you're also going to need a couple of control signals. So we need something to start the conversion, and we need something to let us know that the conversion is done. So I'm referring to that as the start of conversion, or SOC, and the end of conversion, or EOC. This is just a one digital logic signal to let us know the conversion is done and that our converted value in digital is ready to be taken. And we also have this input to begin the conversion. Okay, so let's go ahead and kind of briefly go over each one of these blocks. The first one that we have is a sample and hold. Now, the only job of this sample and hold is to take whatever the analog input is and hold it, to keep it, so that if our analog input changes, which it would with respect to time, we don't want that changing to occur. We just want to take a snapshot of what that analog value is, that voltage, is at that point in time. So let's just say we had like 1.1 volts that was sampled on the input, and then so once this gets the signal from some timing logic, it would keep that value at 1.1 volts so that we can do the entire conversion on that 1.1 volts regardless if our input changed. So maybe our input now went to 1.2 volts. Well, we're still going to be processing this value. So we don't want this analog voltage to be swinging around all over the place as we convert this 1.1 volts into our digital output. Okay, so that's kind of the whole job of that sample and hold. And actually, it's not that difficult of a circuit, we're not going to go over how to create sample and holds. We're really going to keep this more in the higher level algorithmic how an SAR converter works. Okay, so that takes care of the sample and hold. We have this comparator over here. Now, the only job of the comparator is to let us know which of these two voltages is greater than the other. So let's just say we had 1.1 volts here, and we had 1.2 volts over here. So this comparator can compare these two voltages, and the output of this comparison will let us know which of these two voltages is greater than the other. So that's just a comparison that's taking place, and you'll see that as part of the algorithm as we work through it. Next up, we do have some timing and control logic. So the timing and control logic is really just kind of the algorithm. It's just the like a state machine that's stepping through the algorithm, taking the output of this comparator, changing the output over here, and you'll see that as we step through the algorithm. Now, the start a conversion, as I said previously, just tells the timing and control logic that, hey, we want to start converting a value from analog to digital. So we would go ahead and initiate that state machine to go ahead and first do the sample and hold, and then start performing these comparisons. So you'll see in the algorithm that it's going to be a sequence of comparisons that ends up giving us an output. Okay, now we have over here the last piece of this puzzle, which is a DAC, a DAC. Now, previously, let me grab my notes over here. I'll just use this one. Now, previously, we had an analog digital converter. Takes an analog input, gives us a digital output. The analog input is on some range, 0 to 5 volts, some continuously time-varying signal, and then we take that voltage that's on this wire and we turn it into a sequence of ones and zeros over here. Well, a DAC is the same thing in reverse. So let me go over a DAC, and if we understand from the previous portion of this lecture how an analog digital converter works, then a digital to analog converter is not that much more. So let's go ahead and let's take this digital to analog converter, which is oftentimes abbreviated as DAC. Now, for the sake of stepping through this algorithm and understanding the internal workings of an analog to digital converter, we're going to use a very low resolution, 4 bits. That'll be my example. And the reason I'm going to use 4 bits is the process is the same for an 8-bit versus a 4-bit. It's just that it would take me a very long time of sitting here, and practically you'd get bored of it if I did an 8-bit conversion or a 10-bit conversion. So if I do the example from the point of view of a very low resolution, simple 4-bit conversion, it'll be much easier to step through. Now, For that reason, I'm going to lower the resolution of this digital to analog converter to be a 4-bit DAC. Now, the output is going to be analog. The input, however, is going to be digital. So I'll denote that with a bus wire of 4 bits. So we can have values in binary going from 0, 0, 0, 0 all the way up to 1, 1, 1, 1. This is base 2. Or in other words, we can go from 0 to F, base 16. Okay. Now, we still need to define what our range is going to be. Now, for our range, we're going to have 0 to 5 volts. And that's going to be the same as our successive approximation. Okay, so I'm going to show the idea behind a digital to analog converter, what this does, from the same perspective that we will then use inside of our SAR, inside of our ADC. So in order to create an ADC, you need a DAC. Or in other words, to create an analog to digital converter, you need inside of it a digital to analog converter. Okay? And let's go ahead and define the step size for this DAC. So the same rules that we used for our analog to digital converter can be used for a digital to analog converter. So it's the same exact thing, at least as far as the math goes. So let's go ahead and define our step size. Our step size, well, our range is 5 volts. So from 0 to 5 volts, we have a total difference in voltage that we are measuring of 5 volts. And we are converting a digital value of 0 to F, or a grand total of 16 possible values, into a voltage between 0 to 5 volts. So we take the step size and we divide that by 2 raised to the power of how many bits of resolution we have. So 2 to the 4, or 16. And so what that gives us is 0.3125 volts. Okay. So let's go ahead and do some examples of conversions. There we go. Let me grab my red marker. Let's say our input is 0. Let's say 0, 0, 0, 0. Do it in binary. Okay. 0, 0, 0, 0 binary is equal to 0. Base 10. Okay. So if we wanted to find out what the analog equivalent of this is, we're just going to take the value in decimal and we're going to multiply that by our step size. Well, of course, that's going to be equal to 0 volts. So let me call this the analog out and the digital in. Okay, so when we give this DAC an input of 0, we get out 0 volts. Well, that makes sense. Okay, let's go ahead and let's make this the highest value. 1111 base 2, and of course, is equal to F, or 15 base 10. And if we want to know what that analog output would be when you give the DAC 1111, well, you just go ahead and take 15 times 0.3125, our step size, and what does that give us? 15 times 0.3125. Okay, 4.6875. Don't worry that it's not 5 volts. Each converter actually behaves a little differently at the highest value. Some DACs might give you 5 volts, other DACs give you 4.6875. Kind of depends on the topology. But let's just keep it simple and just take the step size, multiply that by the decimal equivalent of your digital input. Okay, so now let's go ahead and let's do half of that. 1000. Okay, 1000 would be 8. Well, what would this DAC produce on its output if we gave it a digital input of 1000? Just take your decimal equivalent to that value, 8 base 10, times 0.3125, our step size, and we get 8 times 0.3125, 2.5. Cool. So half of our range on the output. Okay, let's go ahead and take some other input. Let's do 0110, or 6 base 10. Okay, same thing. If we want to know what our analog output would be from our DAC given a digital input of 0110, or 6 decimal, just take 6 times the step size, 0.3125, and we get 1.875 volts. All of these are volts. Okay? And similarly, if we wanted to take, whatever digital input you have, just multiply that by your step size, and that's what the voltage output. So the whole purpose of a digital to analog converter is to convert from a digital value, or a group of wires representing a digital value, into a single wire that is an analog voltage. Okay? So just the opposite of what our analog to digital converter is, right? Our ADC takes a single wire voltage and converts it to a sequence of wires in digital that represent a digital numerical value on the range of however many bits of resolution it has. Okay, so we're going to use that here. Okay, so in order to create an ADC, we need a DAC. So the DAC gets a digital value. You can see the bus here represented however many bits that our converter is going to be. Let me go ahead and say that we are going to create a 4-bit ADC. Therefore, we are going to need a 4-bit digital to analog converter. Okay. Now, in order to visualize this algorithm as we step through it, the easiest way is for us to set up a table and a graph. I'm going to go ahead and we're going to have time along the x-axis and the voltage output from our DAC is going to be along the y-axis. If you notice, the output from our ADC is really the input to the DAC. Okay? It's going to make a lot of sense in a second. Now, I also should go back over here. And we should define our range for our input to this ADC. Not only is it 4 bits, but it's going to operate on an analog range of 0 volts to 5 volts. Let me see if I can adjust the light just a little bit here. Okay, I think that works. Okay, so we're going to take some analog value on the range 0 to 5 volts and convert that into a 4-bit value. So in other words, the analog digital converter that we are making here looks like this. 0 to 5 volts in and 4 bits out. This is a small V right there. Okay. And for the sake of our example, well, let's actually fill this out first. We're going to establish our min and max. Zero volts over here. Remember, VDAC would be the voltage output from the DAC. So we'll have voltages along here. We're going to have our highest one be 5 volts. We'll split that down the middle. Say this is 2.5 volts. Over here, we'll do 3/4 of 5 volts, or 3.75 volts. And down here we'll have 1/4, or 1.25 volts. Okay, so I'm just breaking this up. The technical term would be Vref. This, of course, half of Vref, 3/4 Vref, and 1/4 times Vref. Okay, so all the way 0 to 5 volts. And as we go through time, as we increase in time, we are going to get closer and closer to our actual value. I'm going to break this up into 4 sections. Okay, that looks good. And along time, we're going to get closer and closer to our value of interest, our VN, and we actually start at the third bit, our most significant bit, and we end with our least significant bit. I know I'm using big B's. Sorry, they should be small b's, but most significant bit and least significant bit. So this is bit 3. This is going to be bit 2. This is going to be bit 1. And this will be bit 0. Okay. Now, we're going to need, in order to run the algorithm, we need to have some test case out here. We need to have some voltage over here. I'm going to use Vin is equal to 1.6 volts. And as we step through the algorithm, we're also going to fill out this table. We're going to see the value written to the DAC. We're going to plot down the voltage output from the DAC. We're going to look at that comparison. So the output from this comparator and we'll see what our bits are. Just to reiterate, we have a voltage input and we're trying to find the digital equivalent to this voltage input. Okay, now to start this process, the first thing, of course, someone goes ahead and asserts this start of conversion. That start of conversion goes ahead and tells the sample and hold, hey, whatever value you got here, grab it and keep it here, because we don't want it changing while we step through the process of conversion. So this is always going to be 1.6 volts for the entire duration of this comparison. Sorry, the entire duration of this conversion. Now, the first thing that control logic is going to do is going to output a value with the most significant bit set high and all other bits set low. Okay, so we're looking at this value over here. It's going to be 1, 0, 0, 0 in binary. Let me erase this 4 because we now know this is always 4 bits for those buses. Okay, so the DAC gets a value of 1, 0, 0, 0. All we do here in the first step is set that first bit high. I'm trying to draw a box around that first bit. Okay, so you start off with everything 0 except for that most significant bit set high. Now we need to go ahead and answer the question of what's the voltage output from our DAC. Well, to do that, all we have to do is take our digital value and multiply that by the step size. As we did previously, our step size is just 5 volts divided by 16. So with 4 bits, we can represent 16 different values, or 0 to 15, and that gives us our step size of 0.3125. So I'll write that up here. .3125. Okay. So this obviously is 8. So 8 times 0.3125 is equal to what? 2.5 volts. Okay. So let's go back to over here. So we are now outputting 2.5 volts. That's all the DAC's doing. 2.5 volts now enters this comparison and gets compared to 1.6 volts. So now we're going to look at the result of this comparison. The comparison ends up with, well, let's go back over here. We're comparing VDAC to VIN. VIN is less than VDAC. Now, when VIN is less than VDAC, we clear that bit. So this first most significant bit of interest here gets cleared. Bit 3 is equal to 0. Okay, so what did that look like over here? So the first thing we did, we set that most significant bit high, and the output from the DAC was 2.5 volts. And VIN, I should also draw on here, is about it is 1.6 volts. And so the output of the DAC was much greater than what we were looking for. Therefore, we clear that bit because this is obviously too high. That's what we said over here. Vin, well, VDAC is greater than Vin. Therefore, we clear the bit. So bit 3 must have been equal to 0. And now, that's going to cause us to go down. So now we're going to go ahead and do the second bit. We cleared that most significant bit, and now we set the next bit. 0, 1, 0, 0. All other bits are cleared. Well, I should say they're unchanged. Okay, so now we have 0, 1, 0, 0 feeding into this DAC. No longer is it 1, 0, 0, 0. It is 0, 1, 0, 0. Base 2. Okay, so what's the voltage output from that DAC? Well, 0, 1, 0, 0 is obviously 4. And 4 times 0.3125, or times our step size, is equal to 1.25. So now we are comparing 1.25 to 1.6 volts. Now you can see that the output of this comparison is going to be opposite of the previous bit. We are now too low. Graphically, we can see this. We're now comparing VDAC to our Vin, and it turns out we're too low. So now Vin is greater than VDAC. And when that's the case, we leave that bit set. So we've already set it. I'm just going to say no change. Bit 2 is equal to 1. Okay, now the next bit of interest that we need to find is bit 1. That bit gets set. The more significant bits stay the same as the previous value, and our least significant bit stays as 0. So we carry these bits. If bit 2 was no change, we keep that. And if it was cleared, then we keep it as cleared. You can kind of see why this is called a successive approximation. Okay, 0, 1, 1 is obviously 6. So the output from the DAC is going to be 6 times our step size, 0.3125. That should be 1.875 volts. So 1.875 volts. So we wrote a 6 to this DAC. We get 1.875. And now VDAC is greater than 1.6. And you see we're going to clear the bit now. So now Vin is less than VDAC. And so we go ahead and clear that bit. So bit 1 is going to be equal to 0. I should have shown graphically before I cleared that bit that this went up to 1.875. We're just above it, just above our Vn, and that's why we ended up clearing it. Okay. Now let's go ahead and find our least significant bit. Now notice bit 3 is 0, bit 2 is 1, bit 1 is 0 because it got cleared. And now we set that least significant bit because that's the bit we're looking for. Okay. 0101. In other words, 5. 5 times 0.3125 is equal to 1.5625. Zero one zero one, which gave us 1.5. 625 volts. Now again we look at this comparison. Well, now we're below our Vn. .5625 is lower than Vn, but you notice it's closer to Vn than our previous bit. So each time as we go through this, we're getting closer and closer to finding what Vn is. You can almost think of this as kind of like a binomial approximation. You're getting closer and closer to where it intersects Vn. It's kind of why I like to show it this way. Okay, but let's do what the algorithm tells us to do. So now Vn is greater than VDAC, And when that's the case, no change. So bit 0 is equal to 1. Should have drawn that in red. Okay, so what's the result of this conversion? Well, at the end of the day, our most significant bit is 0, second bit 1, first bit 0, bit 0, 1. So we ended up with a converted value of 0, 1, 0, 1. Or in other words, 5. Should have finished the graph over here. Okay, so I think 4 bits is more than enough to demonstrate this process of how we successively approximate what our VN is. And hopefully now this drawing makes a lot more sense. We're using the DAC to generate analog voltages. We're comparing those analog voltages to our voltage of interest that we're trying to find, and we find out if it's greater or smaller than it, and at the end of the day, the input to our DAC is the output from our ADC. So that's how an ADC works. At least this type, the successive approximation, or SAR. Okay, so I will probably have a quiz at some point or on an exam. Definitely ask some questions about this or provide a graph and have you fill in the table and perform an actual conversion on an exam. It's not a difficult algorithm. Go over this a few times. Practice doing it yourself. You can always change what VN is. You can try it with VN equal to 2 and see what you get on the output for your converted value. I think with a little practice, it's pretty straightforward, and I think it's very interesting. Okay. Until next time.